So it's about some very weak version of certain conjecture for certain very specific abelian varieties. So if E is an elliptic curve of Q, so it is attached to a modular form, right? Of weight to a certain level, gamma 0 n, where n is a conductor of the elliptic curve, and so in this case we have the Birch-Santander conjecture, which relates analytic invariance of E of Q to certain algebraic invariance. And so I basically have to review this invariance briefly in order to state my results. So because I would have, in order to to prove our main results, we have to go through all these invariants one by one and compute them. So among the analytic invariants, we have the R value, right, at S equals 1, which we know nowadays is well defined. There's an integral of the cusp from F along the vertical path from 0 to infinity times 2 pi I, or minus 2 pi I actually. We have the Nerval period. It's a minimal positive generator of the period lattice attached to a neuron differential. What else? We have the sign of the functional equation, which is just 1 or minus 1. And we have the analytic rank of the L function, order of magnitude of that function. Okay, so that's basically all for the analytic invariance. For the algebraic invariance, so what do we have? We have, of course, the algebraic rank, which is just the rank of the group of rational points. We have also the torsion of this model Veil group, which is a finite abelian group. And we know by Mazur actually all the possible values of these groups. Can take only finitely many possibilities. Then we have the picture for Irish group, which is a torsion abelian group, but we don't know it's finite. So conjecturally finite. And one major overall problem is that this is a finite group. Okay, and also, yeah, of course, we have also the Tamagawa number for any place V of Q. We have the Tamagawa number CV, which is the number of connected components of the points or of the neural model. So it's always 1, except, I mean, for any place which does not divide the conductor and also infinity. Okay. And finally, so we can state roughly the BSD conjecture. So it has two parts, right? The first part is that the algebraic rank is equal to the analytic rank, which is the rank part of the BSD conjecture. And then, if this is true, then let's say in the case, for instance, where the algebraic rank is 0 or the analytic rank is 0, then psi is finite, and we have a certain equality of rational number. And the L value 1 divided by the K which we denote by RE. So this must be equal to the product of the Tamagawa number times the order of Tetrafarovich divided by the square of the torsion. Okay, so that's the second part of the BSD conjecture in rank 0, because I will only be interested, with the formula in rank 0. Okay, so this left-hand side RE, it's a rational number. Okay? You can deduce that from the Manin-Green field theorem. Okay, and so we know very little about the BSD conjecture in general. The few things we know is that if the analytic rank is less than 1, then it is equal to the algebraic rank. That's a theorem of Gros-Zaguet and Coulibaud. Right, but we don't know much if the analytic rank is bigger than 1. What else? Right, and if the analytic rank is 0, then we do know as the second part. If you just look at the p part of these two sides, we know it's true under some assumptions, right? So then the p part of this formula here, of the formula star, which is an equality of two rational numbers, it is known under some assumptions in certain cases. So let me tell you a bit about that. So it's due to Skinner and Urban, and around 2000, on the work of it was our main conjecture for GF2. And one assumption they have in rank 0 to prove this formula is that the residual representation attached to E is irreducible. That's part of the assumption. Okay, so today, as is indicated in the title, I will be interested in the case where this representation is not irreducible. So then you cannot apply this kind of general result. Okay. So that's for what we know. For what we don't know, for instance, I think it seems to me it's not known that if the analytic rank is positive, then the algebraic rank is positive. As far as I understand, this is open. And the main obstacle for proving that is the finiteness of the Tate-Sharp-Ivy. So if the analytic rank is positive, then it means the value is 0. And so it means the p-adic value is 0. And so if you know that it was our main conjecture, it would tell you, the thermal group is big enough. But if you don't have control of the Tate-Sharp-Ivy group, you cannot conclude this implication. So it is open because we don't know the finiteness of Tate-Sharp-Ivy group. Okay, but to avoid having to avoid this problem of the finiteness of Tate-Sharp-Ivy group, we use thermal groups which combine both the Tate-Sharp-Ivy group and the model var group. So we can use the thermal groups, right? So of course we have this exact sequence. And the point is, what we already know how to control or compute is really the thermal group, and not so much the, the Modular group or the Theorem group. So now I'd like to state a very weak version of the BSD conjecture, which may be more easy to tackle. So let us state a very weak form of BSD for thermal group. So this is the FP vector space of finite dimension, and its dimension is related. I mean, this vector space is related to the L value at s equals 1. So for simplicity, to simplify, it's not important. We assume temporarily that P does not divide the torsion of the elliptic curve. First of all, does not. And also P does not divide the Tanagawa numbers for any place. I insist it's just a temporary assumption, and I will remove it a bit later, because in particular I will be interested in the case where my elliptic curve has P torsion. So then under this assumption, we can formulate kind of weak form of BSD conjecture. So it's a very weak form.
P does not divide the Tamagawa.
Oh, yeah, sorry, P does not. Yeah, I assume it does not divide, it divides neither torsion, neither Tamagawa. Yeah. So then, under these assumptions, the fact that P divides the algebraic part of the L value is equivalent to saying that the dimension of the thermal group is positive, or I mean that the thermal group is non-zero. Right? So why is it a consequence of the BSD conjecture? It's because, well, we have two cases, right? First case, if the L value is 0, right, then we expect under BSD that model bay produces something into the thermal group. So model bay give you something. It's non-zero, it's embedded into the thermal group. Okay, so then it's non-zero. Second case, the L value is non-zero, but it's divisible by P. So then we expect under BSD again that the Tate-Shaffer-Average group is non-triggered. Right, because BSD, I think I erased it already. It's here. If P divides that, since P does not divide the Tamagawa number, P does not divide the torsion, so P has to divide the Tate-Shaffer-Average group. That's why I made this simplifying assumption. That's so that's the conjecture I want to study today. This weak form. So so first, it can be formulated even without these assumptions. You would just need to take into account, the denominator and the numerator in the BSD formula. So, what do we know about this conjecture? Well, I'm not sure. I don't know. I would expect we could prove some unconditional statements. One can prove this under some assumptions. For instance, if the residual representation is irreducible. So I have not looked too much into the literature, but you know, the reason why I expect it should be something doable in some cases is because, you know, if P, let's say, if the R value is 0, then we know that the p-adical function is 0, and so we know the thermal group is big. So it would, you know, if you apply some nice control theorem, you would expect P thermal group would be, you know, non-trivial. So I'm not sure if we can really carry out this in detail, but that's my expectation. It will rely on the Mazur main conjecture. Okay, but in any case, what we know about the Mazur main conjecture is, you know, is under this assumption. So it doesn't include the case where the residual Galois representation is reducible. But actually, there has been some recent work last year of Skinner. So Skinner, sorry, yeah, I should write it in order, alphabetical order. Castella, Rossi, Lee, and Skinner in 2021. So what they do is that they prove, you know, some kind of anti-cyclotomic Mazur main conjecture for some E over Q, such that the residual representation is reducible. So it's anti-cyclotomic. As far as I know, it's it should be the first general result about, you know, BSD at Elliptic primes, and so in particular, they are able to deduce some results in analytic rank 1. So some p part of BSD, the rank is 1. Analytic rank is 1. Okay, but there's some assumptions still on the, you know, the residual representation, as they cannot take any residual representation. So remark. So they have some assumptions. On E bar, which is just, you know, when I say E bar is just a p torsion of the elliptic curve as a Galois modular. So the assumption is as follows. So they assume it's, you know, the semi-simplification, semi-simplified, meaning you just ignore, you know, extensions, is isomorphic to a direct sum of two characters, fp phi and fp psi. But phi and psi are characters from the Galois group with p star, which are, but the assumption is that neither phi or psi, when you restrict to the decomposition group at p, can be the cyclotomic decimal character. So that's part of the assumption. So it excludes, in particular, the case I'm going to treat, where one of them is the cyclotomic character, one of them is the trivial character. And furthermore, as far as I understand, they cannot, for instance, treat the case where the analytic rank is 0.
But that case, in many instances, was done by Greenberg and Botzel under the same concept.
I see, yeah. But still,
these kinds of conditions. Yeah.
And in rank 0, you're saying in rank 0, you can, okay, that I didn't know. Yeah, okay. But in positive rank, let's say rank 2, for instance. Yeah. Okay. Okay, so now I can state a bit our results. So so I will, you know, explain what we do in the simplest case where the elliptic curve is just x0, 11. to simplify. And all the main ideas are already there in this case. And the prime we are going to be interested in is prime p equals 5. So this elliptic curve is the elliptic curve over Q, which is given by a certain equation. This elliptic curve possesses a point, which is the point of coordinate 5, 5. And this is a point of order 5. So this point P, it has order 5. And actually, what one can show actually is that the model variable is just that of 5 there. It's cyclic of order 5. So, you know, the reason why it's cyclic of order 5, it doesn't come out from nowhere, is because there is what we call an Elliptic congruence. The reason for the existence P is the Elliptic congruence law. What does it mean? It means you know, the curve from F, which is attached to E, so it's a unique curve form of weight 2 and level gamma 0, 11, which is given as an expansion as follows. So it's Q product of 1 minus Qm squared, product of 1 minus Q11m squared. And let's write that as sum of A and Qn. But the constant coefficient is 0. Okay, so this curve form is actually congruent to the Elliptic series of same weight and same level mod 5. So inside, you know, inside the space of modular forms of weight 2 and level 11, you have the Elliptic series F. So the Elliptic series being given by the following Q expansion, it's 5 over 12 plus certain sum of some variables m, which are prime to 11. Right, and the fact, you know, due to Mazur, of course, much greater generality, is that the form F is congruent to the form the Elliptic series mod 5. And the reason for that is that you know, this constant coefficient here is 0 mod 5. So mod 5, this Elliptic series looks like a cuspidal form, and you know, it has to be this graph because it's unique of this weight up to n log 1. So you know, since you have this Elliptic congruence, we conclude something about the elliptic curve itself. Right? So what does this congruence tell us? It tells us that the F coefficient, Fourier coefficient of F, is congruent to L plus 1 mod 5 for any prime L not dividing 11. Right? And this is just, I mean, AL is just also L plus 1 minus the number of points of your elliptic curve mod M. Right? So it implies that 5 divides that. So 5 divides the number of points mod M for any prime L not 11. Right? So, you know, it doesn't prove that E has a global point of order 5, but it's a strong motivation, right? If you have a point of order 5 modulo any prime, you know, you can suspect that it's a global point, although it's not true, but that's, you can actually turn that into a proof in this case. Right. So that's why the Elliptic congruence, you know, explains the torsion, the 5 torsion we have seen. Okay, and so now, so my goal is to study BSD, the weak version of BSD for this X011, but twisted by some quadratic characters. So let's first see what does BSD tells us about the elliptic curve itself. Right, so BSD just for E itself over Q. So what does it tell us? So first, on the analytic side, the R value we can compute is just 1/5. So as the value was to remember the value at s equals 1 divided by the plane. And the modular symbol computation shows us that this is 1/5, this quotient, right? So okay, that's the analytic side. What about the algebraic side? So the Tamagawa number are all 1 for any v not 11. But at 11, the Tamagawa number is 5. It's basically due to the fact that the analytic valuation of the chain variant, the 11 analytic valuation of the chain variant is divisible by 5. So we have this, Tamagawa number mod 5, which is 0 mod 5. The torsion, what about the torsion? So the torsion we have seen is z mod 5. And now Mazur proved that actually the Tate-Sharifi group at 5 is trivial. That's one of his results in his paper on the SSI ITO. Yeah, I think. So Mazur proved in this paper on the Einstein ideals that the Tate-Sharifi group is trivial at 5. So he did a descent, a 5 descent. Right. So now, what does the BSD conjecture tells us in at 5, at the prime 5? BSD at 5 tells us that 1/5, which is LE, should be the Tamagawa number, which is just 5, and Tate-Sharifi, which is trivial, actually divided by the square of the torsion, which is 5 squared, which is true. So Mazur proves the 5 part of BSD for X011. So now, what about quadratic twists? So we are interested in quadratic twists. Right, so D is a fundamental discriminant. Could be positive or negative, and yeah, I assume also that 11 does not divide. So it's a unique elliptic curve over Q, which is isomorphic to E over Q squared of D, but not isomorphic to E over Q. Which is isomorphic to E over K plus Q squared of D, but not over Q. Okay, so actually Mazur studied this twist and BSD for this twist when D is negative. So Mazur in 1979 studied weak BSD for D of Q if D is negative. So now what I would like to do is to first recall Mazur's result and then move on to the case where D is positive and state so weak BSD conjecture in the case where D is positive. So so let's first do the case D negative. Okay, again, K will be skew sturdy, imaginary quadratic, and there is the following fact that the root number of the elliptic curve ED is 1 if 11 is inert in K. And -1 otherwise. So we will only be interested in sign 1. Okay, for everything we do, we don't want trivial zeros. Right? We don't want this L value to vanish for obvious reasons. It could vanish, but yeah, if it does, it's not forced by the sign. Okay, so the following Mazur proves the following. In 1979, so assume so that 11 is inert. So 11 inert in K. Then 5 divides the L value, the algebraic part of the L value of the quadratic twist, if and only if as the 5 Serma group is non-trivial. That's the result of Mazur. Right. Okay. So now our result in the real case is the following. So again, we will assume the sign of the functional equation is 1.
So for those, sorry, I have a question. For those who sort of view BSD as producing rational points, what can you conclude from this about global points?
I mean, the fact that the Serma group is non-trivial doesn't tell us, is it the model veil or the shell which is non-trivial? We cannot, discriminate between the two. It cannot tell us anything about,
Yeah. So is it still accurate? I'm just going to throw something at you in terms of basically we have no ways when the rank's bigger than 1 to produce rational points other than, right? That remains the case.
Exactly. You cannot magically get construction of points. You can just tell either Shai is non-trivial or the model is non-trivial.
Put another way, if the Hagener point doesn't do the job, we kind of screwed.
Exactly. Yeah, you're right.
Okay, thanks.
Yeah. So okay, what about the real case? So again, the fact is that the sign is the opposite, right? So E. So E, the sign is 1 if 11 is split, and -1 otherwise. So we assume we are in the first case. So our theorem with Junwong is the following. So our theorem is that so assume that 11 splits in K, then first of all, 5 always divides L value, okay, without any further assumptions. And secondly, 25 divides the L value if and only if the five Serno group is non-trivial. So that's the two results. So Mazur, all his paper is about the case where K is imaginary quadratic, except there's one line about the real case when he observes that basically. So I mean, I'm not sure if he observes that, but what he says implies that here. Yeah.
And this theorem applies more generally to some class of modular forms within Eisenstein.
Yeah, right. Only the case of way 2 and prime level right now. But yeah, I hope one can do that in maybe square free level and some other kind of levels in the future. So yeah, maybe let me again talk about this the first fact here. So as I said, so Mazur already knew it. So and the one reason for that, if you want, on the arithmetic side, the reason why it's always divisible by 5 is because of the Tamagawa number here. The reason behind it is 5 divides the Tamagawa number 11 of the quadratic twist. 5 divides that, yeah. So it's a kind of trivial local reason. Right, it's because 11 splits in K's and K locally at 11, it's just Q11. So as Tamagawa number is the same as for E itself. So it's divisible by 5. Okay, so what about the proofs of these two results? So the two results actually rely on a stronger assumption. Result actually. So the case where G is negative, so Mazur proves that the following assertions are equivalent. First of all, 5 divides the L value. Second, 5 divides the class number of K. So HK is a class number. Okay. And third, the Serno group is non-trivial. Right, so it proves these are equivalent. Of course, this result just tells you I is equivalent to 3, right? But actually, we just insert a second equivalent condition. So when D is positive, the following are equivalent. First, 25 divides the L value. Second, 2 for H is a 5th power mod 11, mod the prime above 11. Okay, I will tell you what U and H are. You can guess already. And the third condition is the same. The 5 Serno group is non-trivial. In both cases, we have just inserted like a kind of more explicit condition between the two. So what is U and H? So U, so if D is positive, so again H is a class group, class numbers, right? And U is a fundamental unit. So So it's quite natural, right? That the imaginary case we don't have units, so the only condition is about the class group. In the real case, we do have the same condition. The class group namely is divisible by 5, but it's not. It's only sufficient. It's not necessary. The unit itself could play a role, right? So the condition is that u per h is a fifth power, which is weaker than 5 divides the class group. Right. So how do we prove this stronger result? We just do it by hand. We just prove, first of all, I equivalent to 1 equivalent to 2, and then separately we prove 2 equivalent to 3 by pure unpure thought, let's say, by pure calculation. Sorry for pure thought school. We prove separately 1 is equivalent to 2 and 2 is equivalent to 3. Today I will focus on the first part, right? Yeah, the L value related to some arithmetic invariant. And so the first part, one way to study the first part is use modular symbols. It's not the only way, but it's one possibility. The other part is more classical. It's like descent or Galois homology. Like what Major, the Eisenstein descent of Mazur, basically. So today I will just focus on the first part. So we know that modular symbols provide a way to compute L values. So let me give a model proof of that. So, proof of I equivalent to 2, at least when D is negative. It's not an actual proof, but it's we can turn that into a proof. So the value of E twisted by chi at 1 divided by the plus period or minus period, let's say when it is negative. So chi is the odd character corresponding to D. So it is a quadratic character corresponding to D. So it's an odd character. So this quantity, where E is the elliptic curve, or let me say F, because E would not to confuse the Eisenstein series. So F is a cusp form of weight 2 gamma 011. So morally speaking, this should be congruent to a simple factor times 1 over 2 pi I times the L value of the Eisenstein series twisted by chi 1. Right? Because F, the modular form, is congruent to E2 mod 5. So we expect the L values are congruent mod 5 too. And what is this L value? It's basically up to certain Gauss sums that I will ignore. It's just L chi 1, L chi 0. Which is chi is quadratic, so it's basically the first Bernoulli number twisted by chi squared, which is just basically the class number squared. Right. So if you accept that congruence between modular forms imply congruence between the L values, it gives a kind of strategy for proving that the L value is related to the class number. So actually, this could hold even if D is positive, but the problem is that if D is positive, chi is even, and so the Bernoulli number is 0. So you just get D over mod 5, right? Yeah. So. So if K is even, so the same kind of argument tells you that L of F by 1 is congruent to 0 mod phi. Since the Bernoulli number attached to an even fact in the first place. And so this is an explanation for this kind of phenomenon where 5 always divides their values because of that, morally speaking. Okay, so that's not an actual proof, but you can turn that into a proof using modular symbols. So modular symbols. So what are modular symbols? So since E is an elliptic curve, we can attach a function phi E, which depends on the sign plus or minus, which is a function from Q to Q, which tends a rational number R to the following quantity. So the integral from R to I infinity of 2 pi I f z dz. And you symmetrize that according to the complex conjugation. So plus or minus R I infinity 2 pi I f z dz. So you just have this, and you divide by the appropriate K of omega E plus or minus. And so this is it's a rational number. And actually, so the fact is that phi E plus.
So can you just repeat your comment of your choice of sign? You take which in this definition of this function that you just wrote?
Here.
Oh, there's a now mine.
Yeah. So these are the odd and even modular symbols attached to EM. Actually, the -1 takes value in Z. And the +1 takes value not in Z, but quite. It's just 1 over 5 times Z. So there is a slight denominator. And now, as is well known, the L value is computable in terms of this modular symbol. So the L value LE D is basically just up to a certain easy factor involving square root D maybe is just and the Gauss sum. So I forget about some kind of trivial factor like this Gauss sum, maybe the square root of the discriminant is sum of chi A phi E plus or minus depending on on D, right? Whether D is positive or negative, divided by A of D, where A is in Z of dz star. Right. Okay. So in order to understand this mod a power of 5, you need to understand that mod a power of 5. Right. So it suffices, or it suffices to understand a symbol mod 5 or 25, right? The power of 5. So now this has been studied by Mazur when when D is positive or negative. So let me tell you his result. So theorem of Mazur is that phi, the odd modular symbols attached to evaluated at the rational D over D is congruent to 24 times the integral from Z to gamma Z of the Eisenstein series e to Z dz of 5. Okay, so I need to explain a bit the notation. where we assume that 11 does not divide D, and gamma is just any matrix A, B, C, D in gamma 0. Gamma 0, 11. It does not depend on the choice of gamma. And the fact is that this quantity is an element of Z. Okay.
So that's some arbitrary base point.
Yes, and Z is any base point in the upper arc.
There are two Z, maybe.
Yes, let's call it 0. It does not depend also on the choice of Z0. And so also you can give an explicit formula for that. It's due to Hanmacher. So there exists an explicit formula for this integral Z0 gamma Z0 of C2 Z in terms of Dedekind terms. So, it's very natural, right? The periods of F are congruent to the period of the Eisenstein series. And so using this explicit, formula, the Mazur is able to deduce is, I already erased it, is formula for the fact that the L value is basically the square of the class group mod 5. What about the case where the discriminant is positive? So Mazur also has a result where D is positive. So Mazur proves the following. So remember this odd modular symbol, this even modular symbol. It's not quite an integer, it's as a denominator, but the Mazur proves that if you subtract 2 over 5 to this odd modular symbol, so to this even modular symbol, sorry, it becomes an integer. So this is always an integer, and it gives a formula for that mod 5. So it's just congruent to log D mod 5, where log is a group homomorphism from Z mod 11 star at 5, which sends the generator 2 to 1. Right, so that's also due to Mazur in his Eisenstein paper. Okay. And when I, remember when I said Mazur noticed that 5 always divides the L value, I wasn't referring to that actually. Because if you apply this congruence to the L value, you immediately see it's a 0 mod. Mod 5. Right? Why is it so? It's because so we get that the L value of LED is congruent mod 5 to sum nz mod dz star of chi A and log D. Log D does not depend on A, right? So it's just log D times the sum of all the chi A, and it's 0. Mod 5. So that's the proof that 5 always divides this L value. Okay, so now, of course, we want to go further. We want to study this L value mod 25. So we need to understand this modular symbols mod 25. So we need to go beyond this. So let me state the formula. Yeah. Here is the formula. if formula for is an even modular symbols mod 25. I mean, minus 2 over 5 and mod 25. So here is what works. So there exists a function f, a surjective group homomorphism K2 of z that 11 plus z mod 5 such that for any b over d in Q, in lowest terms, such that 11 does not divide d, then even modular symbols, 2 over 5 minus the even modular symbols, is congruent to, first of all, log d, right? So remember we had this formula for Mazur, so it's log d mod 5. So mod 5, this is what we get, but then mod 25, so it's plus 5 times f evaluated as the sum from I equals 0 to k of the Steinberg symbol 1 minus theta 11 di over di minus 1 or this time 1 minus theta 11. So let me explain the notation. So where, first of all, this bracket here.
Sorry, what is log d actually?
Log d.
So now you want it to be something mod 20?
Right. Okay.
So
So
just mod 5. No, I'm not.
yeah. Right. So what do I mean? I mean, yeah. Yeah. Right, so actually, okay, it's not quite correct. I need to take a combination when the sum of logs vanishes.
Okay.
Well, yeah, to be honest, I restrict these modular symbols to 5 types of homology. So, yeah, yeah, it's a little approximative. Yeah.
Okay.
But yeah, in the end, that's the only term we are interested in. All right. Yeah. So actually, yeah, the formula is for combination of value like that, where all the combination of the log vanishes. Yeah.
Good.
Right. So this is a Steinberg symbol in K here. Okay. And what are the DIs? So DIs. So you write B over D, right? And let's say it's BK over DK. And then you have BK minus 1 over DK minus 1. E0 over 0, which is in Z. So these are the the successive quotients of the continued fraction of B over D. Successive convergence of the continued fraction. Where, okay, if one of these di here is divisible by 11, you just remove the term. Just don't consider it. Yeah. So that's the formula we get. And yeah, just one more minute. So
Sorry, what's the exponent of the first zeta 11 on the right hand side of your congruence?
what's oh, it's mod 25. Yes, mod
No.
20. Yeah.
No, what's the power of the zeta 11? I just can't read it.
Oh, here.
Yeah.
Over di minus 1. I minus 1.
Wait, so is B just not appearing in the right side?
Yeah, exactly. And the right side is just 1 minus zeta 11. Yeah, exactly.
All right, thank you.
Okay, so the last thing I want to say is that this is a little unexplicit, right? Because it depends on the continued fraction associated to B over T, so it's not very explicit. So you can make it, so that is a trick to avoid this continued fraction. So in order to avoid that, we can move to a higher level. So move to level 11D. So you move to modular symbols of level 11D, and basically your Manin symbol, your modular symbol here becomes, actual Manin symbol. Yeah. So basically what we have is a formula for this modular symbol evaluated at Manin symbols, which is not enough for our L function purpose, But if you move to a higher level, then it's enough. Because everything is expressible in terms of Manin symbols. And the last thing I want to say is that, this formula relies on the recent work of Venkatesh and Sharifi on modular symbols and K-theory. So it relies on conjectures due to Sharifi for modular symbols. And in particular, we have to use their work to show that we can indeed move the level, and you have to to be careful about how Sharifi's conjecture changes when you increase the level, for instance. Okay, so that's all I wanted to say. Yeah, thank you.
Any question?
Where does fundamental unit show up in the
So the fundamental unit basically it shows up when you raise it to the power h, right?
Yeah.
Then it becomes by the class number formula product of a cyclotomic unit. Right? And this, this shows up in this Steinberg product when you pass to level 11D, then you will have some cyclotomic units of level D. And if you are careful in your computation of the Steinberg product, in the end, you will get something like that.
Okay, great.
Are there any other questions? So on Zoom?
So do you mean that you use Sharifi's conjecture, or how they prove Sharifi's?
So both. So we use a statement of Sharifi's conjecture. We use also the fact that it's true in our case, but as I said, we actually need it not at level 11, but at level 11D. And for that, you have to use also the techniques they use in that paper.
And I have a question. So you said there are some results on the if the analytic ranks more than one.
Sure. I mean, all these results do not assume the L value is non-zero. It could be rank 2 or rank 4 or whatever. But you cannot produce a global point. You can just say the Selmer group is non-trivial. Yeah. Yeah.
So are there any more questions? Otherwise, thanks, Emmanuel, again.